Hello, and welcome to my reflection on Bayesian Reasoning and Methods. In this presentation, I'll talk about my motivation for taking this course, specifically my interest in randomness. Then I'll compare Bayesian frequentist methods, reasoning, and interpretations of probability and statistics. Then I'll talk about how I actually plan to use Bayesian reasoning and methods. And then in the next video, I'll discuss an example application of Bayesian reasoning. So why did I take this course in Bayesian reasoning and methods? So I got really interested in randomness right about when COVID started. My dad had introduced this book to me, The Black Swan, which Nassim Taleb wrote. And since then, I've read a lot of his works. So there are two ideas that I think are particularly interesting and applicable, especially with COVID, that I'll just discuss here in case whoever's watching this is also interested in randomness. But this is basically a plot showing the turkey problem, at least as Nassim Taleb discusses it. So imagine you're a turkey, and on this y-axis, the variable is perhaps your trust in your owner of feeding you every single day. And the more you live, you and all your buddies are getting fed every day, and you're about 140 trust level on the thousandth day, and you could fit a perfect linear line basically from all the way from the, not a perfect, but pretty good. And you could even say, oh, right here, this is the great the great sleeping or the great vacation of my owner or whatever. You can get really magnified in here. And then all of a sudden, all of this was for absolutely nothing because it's Thanksgiving. That sort of felt very applicable or mysterious during COVID. So that got me interested. And then here's another plot that he included about forecasting. So I definitely recommend getting this book because there's sorts of philosophical, statistical ideas that me as an engineer had never been introduced to. So this got me really into studying randomness. And one of the things that has come up a lot in the books that I've read since then was Bayesian statistics. So I saw that this quarter there was a class I could take in Bayesian statistics. So I just decided to sign up because I think it was a really cool choice. So I learned one thing that I learned when I was taking this class is that the Bayesian reasoning and frequentist reasoning they differ in terms of their interpretation of probability. So I learned frequentist statistics and reasoning in my engineering class, and it was concerned about long-run relative frequency. For example, if you flipped a coin 10,000 times, so on a very long-run basis, what were the relative frequencies of heads and tails on the trials? In the frequentist understanding, you understand unknown parameters as fixed numbers. And the statistics that you get from these from the trials are then the random variables. So when you assign probability, it quantifies the randomness in the sampling procedure. So this understanding makes a lot of sense in some cases, but not so much sense in others, as we'll see in the upcoming slides. The Bayesian understanding and interpretation of probability is different. It thinks of probability subjectively, or has to do with subjective probabilities. The unknown parameters of a population are understood as the random variables. So then probability in the Bayesian understanding quantifies the amount of uncertainty about an unknown parameter. I'll elaborate on this on the upcoming slides. So I'll use a project that I did in my statistical methods for engineers class, which used frequentist statistics to talk about the differences. Basically, I did in 2019, I think this was my sophomore year, I took a frequentist approach to analyzing the Golden State Warriors and Curry's performance when he made at least one shot from 3 feet beyond the arc. So a pretty long shot. It turns out that the Warriors and Curry play significantly better when he makes at least one shot from deep. So it was a little hard at the time for me to wrap my head around the actual understanding of or the reasoning philosophy behind the frequentist statistics here, because they effectively, you understand that the performance of Curry and the Warriors when Stephen Curry makes one shot from 3 feet beyond the arc are fixed numbers. So these performance parameters, score deficit, field goals made, field goals attempted, and points, and game score plus minus. Basically, these things I have over here on the right. Those are fixed numbers if Stephen Curry hits one shot from 3 feet beyond the arc. So that just doesn't make too much sense philosophically. It certainly does in other cases, such as if you do a basic machine process or a computer aided thing and you have 10,000 trials, maybe there is a fixed number of errors in that 10,000 trials, and then you're just seeing of those 10,000 trials, is this a statistically significant sample? But in this case, I don't really think that if Stephen Curry makes a long shot, that all of a sudden the Warriors and Curry are operating on this new fixed performance parameter. So it turns out that the Bayesian understanding of probability and statistics in this case makes much more sense. So think about games in which Stephen Curry hits at least one 3-point shot from 3 feet beyond the arc. Now, is there performance parameters, so their score deficit, field goals made, field goals attempted, and points in the game, are they fixed numbers? Or are they going to be a large range of numbers? Probably it's going to be based on a bunch of different things. Are they home or away? Who's playing in the game? Things vary quite a bit, and so it makes much more sense to say, well, we subjectively believe based on what we know and the data that we get that their performance, so those performance parameters, can be in between, like in this range, or they have a mean around here, but it's much more subjective randomness. So we understand their performance to be random variables. I think this makes much more sense. So what we've seen that the frequentist reasoning works much better when things have to do with long run relative frequencies. So coin tosses, rolls of dice, defective samples in a computer-based machine process, or just computer tasks in general. Basically anything having to do with the long run, very automated, very repeatable things. The Bayesian reasoning makes much more sense in things that are not very repeatable, such as games in which Stephen Curry hits at least one deep three. Not very repeatable. Makes much more sense for the Bayesian response. Football games, so a matchup is much more. It's much more to say that the outcome of this game is a random variable, but we subjectively believe that it'll be this way or another way, rather than say the outcome of this game is a fixed number, and we're just trying to make sure if the sampling is right. Another thing that makes more sense in the Bayesian framework, or like elections, weather, extraterrestrial life, and just things where probability is subjective. So in this section, I'll discuss how I'll use Bayesian reasoning and methods in my own life. In the past section, I hope I made it clear that I learned about it partly because I was interested in randomness, and I learned that it makes much more sense in some cases. But what would I actually do with it? So I think one place where I'll use Bayesian reasoning and methods in my own life is to answer questions like these. So I'll walk through this question. I got this question from Thinking Fast and Slow by Daniel Kahneman. So a cab was involved in a hit and run accident at night. 2 cab companies, the green and the blue, operate in the city. You were given the following data. 85% of the cabs in the city are green and 15% are blue. A witness identified the cab as blue. The court tested the reliability of the witness under the circumstances that existed on the night of the accident and concluded that the witness correctly identified each of the 2 colors 80% of the time and failed 20% of the time. So the question is, what is the probability that the cab is blue? So they did this study on a group of people. So the most common answer from the survey respondents was 80%. So I'll let you think about what your answer would be given this information, and then we'll move on. But I guess to just point out that this 80% correlates to this information here. So how often the witness gets the identification correct. They basically ignored this data. So what would your answer be? So the researchers then asked the survey respondents a different question, or actually the same question but with a different first part. So they replaced that first part and said that the two companies operate the same number of cabs, but green cabs are involved in 85% of accidents. They found that even though this is effectively the same problem in terms of numbers, the answers that the probability that the cab was blue were much, much lower. So what does all this point to? I think it points to the idea that this sort of problem is hard to answer, but it definitely has to do with subjective probability. There are lots of cases that you can use Bayes' rule, as we'll see here on. So maybe this will show just one aspect of how Bayesian statistics is powerful. So what is Bayes' rule? Effectively, you get a posterior probability. That's what you're concerned about. So the probability that a hypothesis is correct given evidence that you observed is equal to the likelihood. So the likelihood of observing that evidence given the hypothesis was correct times the prior scaled by, this is basically just a scaling factor. So it's really, really powerful, and you can definitely YouTube it and see just how cool it is. But you can use this simple formula, construct a Bayes table as I did here, and come up with the posterior, so the probability that the cab was blue. So just discussing this Bayes table here. So the prior that the cab was blue, basically you didn't get any data from the witness. Would be 18 in both examples. It would be 15% chance that the cab was blue and 85% that the cab was green, just based on operating in the city, right? Because I think in one example, 15% of the cabs were blue, the other 85% of the cabs were green. And that's the same as saying 85% of the accidents come from green cabs, and 15% come from blue cabs of accidents that have cabs in it. Then the likelihood has to do with the data from the witness. You multiply these two together, scale it by this number, and you get this posterior solution. So this is your correct answer. So you can see how this is sort of powerful because it answers a question that we're not good at answering. So what was actually happening here? In part one, we had a statistical base rate, which had to do with the percentage of cabs in the city, and people generally underweight this. So and even sometimes neglect it. As when I first saw that question, I definitely did, and relied on the witness information. But in part two, when you hear that the green cabs are terribly reckless and getting 85% of the accidents, that's a causal base rate, and we actually use those causal base rates much more. So even though it's the same problem, we understand it differently. And this points to a bigger idea, is that even if you understand statistics, like frequentist and Bayesian statistics, we still, humans, we're not, I don't think, understand probability and randomness and statistics all too well. We don't always work well with numbers. So that's when you actually implement the methods that you learn in Bayesian reasoning and methods to solve problems like this and deal with other problems of subjective probability. So I think dealing with real world problems like this using Bayesian reasoning and methods is really powerful. In the next video, I'll show a real life example application of Bayesian statistics using the NFL pick and pool I made